One of the ways we can find more out about a chemical, for example its formula, is by using analytical techniques to calculate an empirical formula. Now, an empirical formula we can calculate from reaction masses. So, for example, if I reacted magnesium with oxygen and I measured how much magnesium I put in, and I reacted it, having weighed my crucible, and I discovered that I had a change in mass due to the oxygen which had been added to the magnesium during the reaction, I could make the assumption that that change in mass was the oxygen. So, having a mass and knowing that different elements have different relative atomic masses, we can take 24.3 and 16.0 for those. We can work out the number of moles of particles of magnesium that we put in and the number of moles of particles of oxygen that have reacted. So that would be mass over relative atomic mass would be 0.5 over 24.3. That would give us 2.06 times 10 to the minus 2 moles. And this one would be 0.332 over 16.0, and that would be 2.07 times 10 to the minus 2 moles. And given that we're going to have a little bit of error in our experiment, those values are so close together that we're going to say, well, they're basically the same value. Okay, so as they're the same value, we can say that our ratio of moles, or our molar ratio, is going to be, for every 1 mole of this, we're going to get 1 mole of this. And then we can say, okay, well, that gives us an empirical formula of MgO. So here's another slightly more complicated example. If we have aluminium and chlorine, and we react those together, again we could measure that we've put 0.25 grams of aluminium in, as our mass, and we can weigh the substance before and after, and we can find that we've used 0.987 grams of chlorine. We know that we have a relative atomic mass for aluminium of 27.0, and we know that chlorine is 35.5. And again we can do the moles. We can take 0.25 over 27.0, that gives us 9.26 times 10 to the minus 3, and then over here we would go 0.987 over 35.5, and that would give us 2.78 times 10 to the minus 2. And so we've got different numbers here, and it's not obvious just by inspecting them what's going on here, but you can see that this one is definitely smaller than that one. And I would take the smallest number, and we would say, okay, if we want this molar ratio, if we want this ratio of moles, then what's the easiest way to go about this? Well, the easiest way to go about this is to change one of these numbers into 1. And I would usually go with the smallest. So if we want to change this number into 1 for our ratio, we just divide by 9.26 times 10 to the minus 3. And so that's going to give us the number 1. And because we want the ratio of this to this, we're going to do exactly the same to this side of the ratio as we did to the previous one. We're going to divide that also by 9.26 times 10 to the minus 3. And what we find by doing that is that we have a number here which is pretty much makes no difference, 3. We have a ratio of 1 to 3. So our empirical formula would be AlCl3. Sometimes we don't get nice round numbers, we might get some fractions. So let's use gallium oxide as an example, if we take gallium and oxygen and we react them together, we might take 0.4 grams of gallium, we might react that, and we might find that 0.138 grams of oxygen is added to it. That's our masses. We can then take our relative atomic masses of each of these, which would be 69.7 and 16.0, and we can calculate the number of moles, which would be 0.4 over 69.7, and that will give us 5.74 times 10 to the minus 3 moles. And then over here we would have 0.138 over 16.0, and that would give us 8.63 times 10 to the minus 3 moles. And so again, the ratio isn't amazingly obvious. It's not particularly clear what we do here, so we're going to divide by the smallest one, which is the one here, the gallium on the left. So we're going to divide by this number here, 5.74 times 10 to the minus 3. We're going to do that on both sides. And that is going to give us the numbers 1 and here 1.5. Now the temptation here is to round this to 2, and that's not the right thing to do, because we know that 0.5 is a fraction which is a half, so we're basically saying 1.5 here. So for 1 atom of gallium you get 1.5 atoms of oxygen. That's actually something that we can put into a whole number ratio, so we would multiply out the fraction. So if we have a 0.5, if we have a half, we're going to multiply by 2, and that will turn this into a whole number. And because we've multiplied by 2 over here, we're going to do the same here, and we end up with a ratio of 2 to 3. And that means that our empirical formula is going to be Ga2O3.